Okay, recall that revenue equals demand multiplied by price. Demand being the number sold and price being what you charge per unit. So if you multiply how many you sell by how much you're charging, you get the total amount of money you take in, which is your revenue. Now we could, we have a situation where we have the demand function, P equals 40 minus 0.02 square root of x. And we know this is the demand function. X is the demand, P is the price. P is not profit, P is price. This is lowercase p. We do have profit. That's going to be a big uppercase P. I've exaggerated the size here, but I have put two stems on that P to distinguish it from the lowercase p. And I made this one really small, this one really large, just to emphasize that fact. In any case, if we multiply then the demand, X, times the price, P, we're multiplying X times 40 minus 0.02 square root of X, and that's our revenue. Now we could maximize our revenue. When is it maximized? Well, when is any function maximized? When its derivative equals 0, because that's where the slope of the graph levels off. That's the critical point. And r prime goes from positive to negative, because if r prime, which represents a slope, goes from positive, that means we go from upward to negative. So we go from upward through 0 at the critical point, and then we go to negative. That means we have a maximum. This is your first derivative test. Your first derivative goes from positive to negative. Or r double prime negative. Now, r double prime is the rate of change of the derivative. If r double prime is negative, that means the derivative is decreasing, as it would be. There's a critical point here, and the graph is climbing here but leveling off. So we have a positive but decreasing slope, and then going back down, so we have now a negative slope that's getting more and more negative. So that would be the test, that would be the characteristic, of the second derivative. It would be negative at a maximum point. It would be positive at a minimum point, just as the first derivative would go from negative to positive. Okay, well, we're not asked to find the maximum revenue, but I just mentioned that's how it would be done. What we're asked to find is the maximum profit. And profit is revenue minus cost. How much money you take in minus how much money you have to spend to produce or purchase or whatever you do to obtain these X items to be sold. So that's easy. Profit, capital P, equals revenue minus price, minus cost. Let's try to contrast the big P with the little p, but I don't have a little p here, I have a C. So this is cost, revenue minus cost. Okay, revenue is what we found here, X times 40 minus 0.02 square root of X, and cost, we are also given the cost function. This information is provided in the problem, as you can see by looking at the document with the problem. Cost is $3,000 plus 4x. That means it costs us, say, $3,000 to set up our machinery, and then every item that we produce costs $4, so the total cost is the $3,000 to get set up, plus 4 times the number we expect to sell. Okay, so our profit function is this minus this, and we simplify that. We get 36x minus 0.02x to the 3 halves minus 3,000, and the simplification is very straightforward. We simply multiply through by x here, getting 40x minus 0.02x to the 3 halves, and then we subtract this whole quantity, negative 3,000x and a negative 4x. So we get this, and we want to maximize this. Well, we maximize this just the way we maximize anything else. We take its derivative, which in this case is 36 minus 0.03 square root of x. The derivative of x to the 3 halves is 3 halves x to the 1 half, or 3 halves square root of x. 3/2 times our 0.02 gives us the 0.03. And obviously the derivative of 36x is 36. There's our first derivative. We're going to set that equal to 0 in a minute to find our critical point. Now, and having found that, we could use the first derivative test to see whether at the critical point the function goes, or the derivative goes from positive to negative or from negative to positive. Alternatively, we can take the second derivative, and that's very easily done. 36 is constant, so it has 0 derivative. And square root of x has derivative 1/2 x to the negative 1/2, or 1/2 square root of x. And then dividing the 0.03 by the 2, we get negative 0.015 square root of x. So there's our second derivative. Now, critical points occur when p prime equals 0. Here's the expression for p prime. We set it equal to 0 and solve the equation. And we get x equals 1,440,000. Okay, we're going to make a lot of these at $4 a piece. It's going to cost us a lot of money to make them, but hopefully we're going to be able to sell enough to recoup that investment. And also the $3,000 it costs us to set up is very small compared to the cost of producing all these items. Okay, so we could use the first derivative test. The first derivative is going to be positive when x is smaller. As x gets bigger, the first derivative is going to reduce to 0. The bigger x gets, the bigger the negative gets. It's going to reduce to 0, and then it's going to become negative and get more and more negative, meaning we should have a maximum to this function. Let's check it out. Okay, our second derivative test is really easy to apply. We have a negative over square root. Square root has to always be positive unless it happens to be 0, but we're not going to make this thing if we're likely to sell 0 of them. And that would be a completely different situation. So the fact that x can't be 0 is not a big drawback here. Okay, so negative 0.015 over square root of x. This is always negative. Negative is a negative here. And this is always positive, so this is always negative. Our second derivative always being negative means, again, we have this situation. Increasing function up toward our critical point, but decreasing in slope means we have a decreasing derivative, and so forth, as I explained previously. I just decided I don't want to go through that again. Okay, you don't want to hear me go through that again. Go back and replay my previous explanation if you didn't get it. No point in making you sit through it twice if you got it the first time. Okay, so this is always negative, so certainly it's negative at the critical point where x equals 1,440,000. That means then that we have a maximum when x equals that number. And our maximum profit then is p equals 36x minus 0.02x to the 3/2. X equal to this, so we have 36 times this minus 0.02 times the 3/2 power minus 3,000. And it looks like I left my minus 3,000 off here. It doesn't make a lot of difference. It doesn't justify leaving it off. Didn't write it down here, although I included it here. Okay, well, we've plugged in now to our profit function, which is still this. And we evaluate this, and I believe we get something like 17 million. So we did sell enough to recoup our costs, but yeah, we didn't exceed it by all that much. We took in 52 million in revenue. Actually it's 52 million minus 35 million, which is 17 million in revenue. And actually that's not right either. Forget I said that, because this 36x includes the negative 4x cost. So we get $40 a piece minus $4 is 36. But then we have our minus 0.02x to the 3/2, and we don't want to get into analyzing that. That would just be confusing at this point. Okay, so in summary, we've got a our demand function, our cost function. From that, we get our revenue function, and then our profit function. We take first and second derivative of the profit function, use them to determine where the maximum occurs and confirm that it is a maximum. Here's our result, and our profit is 17 million.